Hi guys, so today I am going to make one video for COT5405 for the assignment of lower bound, which we have to solve with the help of comparison based sorting. So first of all, we will see the problem statement. Let's see. So here in this problem statement, the element distinctness problem asks if all n elements in a given array are distinct. So we have to decide whether all the elements are distinct or not, if there is any kind of duplicate exist in this array even at one pair. So we have to decide it first. So if all the elements are distinct, then we will get one output as yes. Otherwise, we will get the output as no. So more precisely, we can say the model of computation here is the comparison based sorting. So we actually have to compare two numbers, say x and y, in constant term and answer if x is less than y or equals to y or greater than y. So if x is less than y or greater than y, then it's fine and we can say it as distinct element. But if x is equals to y, then the output will be no. So the problem can be easily solved in order of n log n time via sorting. And we have to prove that the lower bound of the problem is also the same, because we can't optimize the problem further. That is actually the lower bound of the problem. So order of n log n is the best case in this problem. So let's see then the example of the problem. So here in this element distinctness problem, first we will take one input where we can take a sequence of numbers. Let's say we are taking a sequence of numbers of x. Here the elements are x1, x2 up to xn. Then for output, we will get one yes if all x index I are distinct, and no if at least one x index I equals to x index j. Here I and j are indexes, so I and I not equals to j means where those two are different numbers. So even if there is at least one pair of different number, then the output will be no. So again we are claiming that the time to solve the problem with the help of decision tree model will be omega n log n. So now I will discuss about what I am going to discuss in this video. So the outline of the video will be the main concept of lower bound, which we are going to solve using the comparison based sorting. Then we will discuss about decision tree model and why sorting lower bound technique doesn't work, and some new lower bound technique. And also we will discuss about extended model for algebraic decision tree. So now let's see about the main concept of lower bound comparison based sorting technique. So here suppose when we see all the sorting algorithms, let's say for insertion sort, the running time is order of n square, but it's too much, right? So we can optimize it. So if we want to optimize order of n square, then we can get some better running time, which is order of n log n. So a merge sort is actually have that type of running time. So we can say the running time of merge sort is optimal. So here we just have to find whether that order of n log n is the lower bound of the algorithm or not. Like whether any new technique can go below that time or not. So now we are taking one unsorted array. Let's say there is 21, 35, 18, 11. So after sorting, we will get one sorted array where it is 11, 18, 21 and 35. So here actually what happens, if we see all the sorting with respect to their index, then the first element goes to the third place in the sorted array. So 21 goes to the third place, 35 goes to the fourth place, 18 goes to the second place, and 11 goes to the first place. So in this way we got one permutation of the number. So actually what happens, when we give input of n numbers, then we will get a permutation of 1 to n numbers, and the best case will be the order of n log n. So now let's see about the decision tree model. So here in this decision tree model, we were taking one input which is actually a sequence of number from x1, x2 up to xn, and the so here we are just breaking down what we have actually done here. So here the program is labeled tree, this one is a label tree, and the non-leaf node labels are like the format of the non-leaf node labels are I is to j. So here the root node, this one is written as 1 is to 2, which is actually I is to j, and the leaf node label, here we can find the values of the output. And for the edge levels, here all those operators are there for which we can find out the relation between the leaf node and the non-leaf node. So we have used so many operators like less than, greater than, not equals to, greater than, equals to, less than, equals to. So in this tree we will first see that in this node it is 1 is to 2, and then if we traverse in this direction, then we can see that it is less than, equals to, and it is written as 2 is to 3. So how it is executed? So the execution always starts from the root, this one, and at node it is labeled as I is to j, here it is as 1 is to 2, and all those xi is compared to xj. So here all those indexes will be compared to each other, and then we will find how to sort the lower bound. So in the sorting problem, we are taking one input which is from x1 up to xn, and we can get the possible answers of n factorial. So each possible permutation of x. So from this we can say the program tree must have greater than n factorial leaves, because for the program tree there will be some leaves where the values of xi and the xj will be equal. So to have the yes answers, or to have that all those distinct elements, the program tree at least have n factorial leaves or greater than n factorial leaves. So again, if we want to calculate the time taken to traverse the tree, we have to measure the height of the tree, and which is log of n factorial. So we can also tell as omega of n log n. So we can say the answer has n factorial possibilities. So we can say the answer has some high information because there are so many possibilities. But in element distinctness, there is only two answers. Either all the elements are distinct, so we will get the output as yes, or there is at least one pair of duplicate for which we will get the answer as no. So even there is at least one pair of duplicate, we will get the answer as no. So next we will find the strategy needed to solve this problem. So here the tree must have n factorial leaves, which will give the yes answers, and we will also use n dimensional geometry here. And also the time needed to solve the decision tree is omega of n log n. So now we will overview the proof. First we will interpret what we are actually doing here. So here we are taking one input x, where x is actually x1, x2 up to xn number, and we can also consider all those things as point in n dimensional space. So this is actually restricted here, and these restricted instances are unit n cube, but here we are taking as unit n square. As we know, the running time for sorting is n square. So, and also we are assuming the value of xi will remain in between 0 and 1. So now we will assume some claims, and then we will prove all those to finally get our desired result. So first we are claiming let RL instances for which leaf L is reached on execution. So here we can say that RL is convex. So if RL is convex, then we can also say that it is connected. Then the second claim is let X is one input where we have X1 up to Xn distinct elements, and Y is another array where we have Y1 up to Yn non-trivial permutation of X numbers. So Y is basically the permutation of X, all those numbers X contains. Then we can say that X and Y must have reached yes leaves. So it is common if X, all those elements in X are distinct, and Y is actually the non-trivial permutation of X, then they would definitely have reached to the yes leaves. And then the last claim is if the number of yes leaves is greater than or equals to n factorial, then the time will be order of n log n. So let's first prove the first claim. So here we have taken one coordinate, which is x1 and x2, and we have drawn one square here. So here along the diagonal, all the values of x1 and x2 will be equal. So along the diagonal we will get the output as no, but except the diagonal, the rest part of the square, we will get the solution as yes, because for the rest part all those elements are distinct, only along the diagonal they are equal. So next we will find out what is actually a connected region. So a region R is said to be connected if for any points x, y which belongs to the set of R, there exists a path from x to y passing entirely through R. So we can assume if there is one region, suppose let me draw one picture. Suppose this is one region called R. There is one point x and one other point y. So if we connect these 2 points, then the entirely path lies in R. So then we can say it is a connected region. Okay. For the next, we will find out what is convex region. So a region R is said to be convex if for any points x1 belongs to R, the straight line path from x to y passes entirely through R. So here we are seeing almost the same thing, like if x, y are 2 points which actually are the subset of R, and the straight line path from x to y passes through the R, then we can say that it is a convex region. So it is common sense that if the region is convex, then it is also connected. So you can also give some example of convex objects like cube and sphere, and in that way we can in cube or sphere, if we consider two elements and we join them with a straight line, then the line will be entirely lie on the surface of the cube or sphere. So that means we can say that it is a convex region and also it is connected. So again we will find one example of connected region but not convex. So there is two kind of example. One is if we consider one kidney shaped object or one torus shaped object. So I have drawn one torus shaped object. So in this like in this drawing, x and y are two different points in R, and when we have connected both of them, then the line, like it is actually connected. We can see that x, y actually connected and both of them actually lies on R, but the entire line doesn't go through R. So we can say that it is connected but it is not convex. Okay, so next we will see the proof for also the first claim. So in this proof again we are taking x for the input as x1 to xn and y for y1 to yn. These two be 2 points in RL. So for execution 1, if we like take one x, then we can say that L is reached. It is natural because x lies on RL. So if we take x, then we can say that L is reached. Again, if we take y, then we can also conclude that L is reached. It is also same as x because y also lies on R of L. So if we consider y, then we can conclude that L is reached. Then we will take another instance where we will see that Z is another point which is Z1 to Zn, and here in this Z we have actually multiplied lambda with x, and we have considered the raised value of the region and multiplied it with y. So here like if we consider one convex region and if we draw a line, then we can divide the region into two parts. So suppose one part is lambda and the rest part is 1 minus lambda. So we are multiplying that lambda with x and the rest part with y. So here we are assuming the value of lambda must lie between 0 to 1, and z is on the straight line x, y. So here let the root level is I is to j, and suppose we are considering the less than branch in this execution. So first if we suppose if from root we are okay, let me see. Okay. So if from the root we are going to the less than branch, then we have to traverse only on the less than branch, otherwise we have to go back. So it is common sense. If we have taken the less than branch for execution 1, then for execution 2 the less than branch will be taken. So then we will check whether xi is less than xj or not, and yi is less than yj or not. And then if we multiply it with lambda, like we will multiply this one and this one, and then we will multiply this one and this one here. So as xi is less than xj, so we can say that xi will be less than xj, and also this one yi is less than yj, so also it will be less than that. So we have actually we have done the summation of the less than objects in this way and the summation of the greater than object in this way. So we can say, as we have taken the zi in this format, so we can say that zi is less than zc. So the less than branch is also taken for execution 3, which is also following the same logic. Similarly for other branches reaching L. So finally we can conclude from here that RL is actually convex. So here in this way you can prove this one, that where at RL instances for which leaf L is reached at execution RL, so we can conclude that RL is convex and it is also connected. So here we have proved that the solution has reached, so definitely that means RL is convex. And previous that we have discussed what is actually convex region and what is actually connected region. Okay, so next for this claim which is x where we have taken this array and we are checking and we are considering that all the distinct elements are there, and also y is a non-trivial permutation of x. So now we will prove this one. So for this proof, first we are assuming that x consists of all distinct values, so the answer of x will be yes, and y is some permutation of sigma of x, so the answer of y will also be yes, because x, if x gives us yes answer, then y is actually the permutation values of x, so it will also give us the yes answer. So now let's see the proof. So we will prove it by contradiction. So we will suppose that x and y reach same leaf L and RL is connected and there exists one point in path P from x to y entirely through L, means it is also like it is connected. So then we will show that the point Z which lies on P, and for Z the answer will be no. So we will do the proof by contradiction, and then we are again doing one subclaim. So we are thinking like there exists ij such that the value of xi is less than xj and the value of yi is less than yj. So again we are defining one function, that f of w, where the value of f of w can be calculated if we subtract the value of wi from the value of wj from wi. And also we are considering that f of x is less than 0 and f of y is greater than 0. Okay. So, by the mean value theorem, the point z which lies on P such that f of z is 0, so we can say that zi is equals to zj. So the answer of z is no. So that means it is not distinct. We get one duplicate value here. So we have done the contradiction. So from that contradiction we can prove that which we have assumed first, that x consists of distinct elements and it will give the answer yes, and y is the permutation of sigma of x, and y also give the answer y yes. So this one is right. From this contradiction we can prove it. And for that subclaim we can do one calculation. So here we are suppose we are assuming that xi is less than xj and yi is less than yj. So here the value of x is 0.8, 0.2 in this way. The value of sigma of x is in this way. So there is no duplicate pair. And then we are taking the permutation of x as pi x. So here this one is sorted. So we have written as 0.2, 0.5, 0.7, 0.8, 0.9, and we are taking the permutation of y as pi y, which will be 0.2, 0.8, 0.9, 0.9, 0.5. Okay, so here we will calculate, like for 0.2 the value is also 0.2, so we have written in this way, and for 0.5 the value was 0.8, so that's why we have written as 8. So in this way we have calculated the chart. So then in this way we first prove the claim for pi x and pi y, that if I is less than j, then pi of xi is also less than xj. Okay, so here we have proved this one, like if the value of I is less than j, then the value of pi of x of I will also be less than pi of x of j. So, and y cannot be increasing because y is actually the permutation of x's value. So if the value of I is less than j, then the value of pi of y will be greater than value of pi of y of j. So in this way we have so now we can just map back the ij, like we can just check all these things and this one for all those values. So from this proof we can actually prove this subclaim, that there exists ij such that xi is less than xj while yi is okay, so I think it will be greater than y is greater than yj. So this one is the main theme, and then we can go for some summary, that the instances. Okay, one second, I think we have one more proof left. So number of ES leaves, if that one is greater than n factorial, then the time will be sigma of n log n. So from these two proofs we can say that the number of ES leaves will be greater than n factorial, and to calculate this the time will be omega of n log n. So from summary we can say that instances visiting any ES leaf from a connected region in instance space, and no instances partition the instance space such that the distinct permutations are not in same connected region, and also the number of ES leaves must be large. And finally what we actually were trying to prove, that is the running time for this algorithm will be sigma of n log n. So now we can see one more example for this. We can just call it as extension. We can see one algebraic decision tree. In the decision tree, we have used the less than, equals to and greater than operators. We can use another operators, but in this case we have used only these three. So first we are taking one input, which is actually x1 square plus x2 square minus 25. So the action will be, first we have to evaluate the level expression and compare it to 0. So we will assume that x1 square plus x2 square minus 25 will be 0, and then we will choose the branch accordingly. So the expression is linear, and okay, one second. So for expression, linear expression will hold the previous results, and for non-linear expression, the intersection of constraints can produce disconnected region. So in this case we will find the algebraic tree lower bounds. So first we will consider one decision problem where the inputs are x1 up to xn, and suppose we are considering A is an algebraic decision tree. So here that algebraic expression is some fixed constant d, so the value of d will be 2. Suppose no partitions the instance space into y, no means the result no, so no partitions the instance space into w connected region within each of which answer is yes. So for this the time we need to complete that problem will be omega of log w minus n. So d appears in the constants in omega, and for decision tree omega log w, it will be actually a complicated algebra and it won't help much. So for element distinctness problem, we will actually consider this one, the omega of n log n time. So for to prove it, we can consider like one leaf, which is actually a small number of connected regions. In normal case, we just consider one leaf as one small node, but it is here a connected region, and we will use the algebraic geometry to count the number of connected regions induced by degree d constraints. So we have to use the algebraic geometry to find out the degree of d constraints here. So we can, from all these things, we can conclude like lower bound theory tells us when to stop searching for better algorithms, because it is the best case. After this, the algorithm cannot be optimized more. That's why it is called the lower bound. And also it has a deep connection with mathematics. So that and not only mathematics, it has connection with so many other fields. So that's why we can conclude that the algebraic tree is very useful to solve the lower bound problem. And for completing the lower bound traversing, we need sigma of n log n time. So this one is my assignment for COT5405. Hope you understand what I am trying to say here, and yes, thanks for watching.